Hi, welcome to this lecture on environmental adaptation of animals. Now we will focus on the oxygen and carbon dioxide physiology, which means respiration and circulation. How to carry enough oxygen for the tissues and how to carry away carbon dioxide waste products. And if you take a bachelor level animal physiology textbook, you can see that, okay, there's a human lungs and then we have four-chamber heart to form the circulation. But we have to remember that we have plenty of animals that are aquatic. So there are plenty of different ways to make this carbon dioxide, oxygen respiration happening. So on the orange over here, you can see the Christmas tree worms on the coral reefs. They are breathing the water, oxygen from the surrounding water. They have some kind of chills. And then we have a beetle that is carrying an air bubble. And as a layman, we would say that, okay, this air bubble is oxygen store that is carrying, taking from the surface when diving, and then using the oxygen from the bubble. But soon you will learn that actually this bubble is also chill. So it's used for respiration. Okay. The problem in this part of the respiration is that we had to deal a little bit on the physical chemistry. So it's a little bit more complex than just having the lungs and then the circulation, etc. First of all, the problem exists that the oxygen is essential, but it's only working passively. So you can't collect from the surrounding oxygen molecules with some transporters, because there are no transporters on this planet for oxygen molecules. So that means that your cells and your body must have condition where the oxygen wants to go in your body and in your cells. And furthermore, we had to expand the diffusion. So it's not in the gases, they are not always going on the lower concentration. So unlike having high salt and low salt solution, and then you have diffusion, so there's a concentration gradient that is affecting that, okay, there's a flux of this salt on the lower concentration. It works in the aquatic solutions, yes, but when we have gases, it's a little bit different. We had to expand it for chemical potential. And so in the solution, we can have gas bubble, where for example, oxygen is surrounded by other oxygen molecules. They are together, but they can be dissolved, which means that around each oxygen molecule, there's layer of water molecules. And it can be even bonded. So that's why we have hemoglobin. And in this binding is that it disappears. So in your blood, there are no gas bubbles. And that's a good thing. And it can be either dissolved or bonded in, for example, hemoglobin, or metabolized in case of carbon dioxide. And that affects quite drastically on the chemical potential. But it's easy to understand it when we are thinking on the physical chemistry on partial pressure. I try to be as simple as possible. And so partial pressure means that, okay, what is the pressure of not all the air around you, but the air of oxygen in the air around you. And for that, we had to think first on the ideal gases. So ideal gases, we have universal gas law. That is something that you have learned so many times in your education, but quite often we can't remember what was the right order of these letters. So there's pressure, volume, molar quantity, this gas constant R, and then the temperature. And the idea is that, okay, there is a relation between the temperature and the pressure. Over here we have a fixture. On the left hand side there is about 0 degrees Celsius, and then on the right hand side there is quite warm aquatic solution. And you can see that the pressure from the bottom to up, it will increase when you are heating up the gas. Or if you are putting it in smaller chamber, so in the front the volume is a little bit larger than in the back, it's a little bit smaller. So it practically just means that the gas pressure is higher in warmer temperatures and in small chambers. Okay, it's not so difficult. And it's as simple when we are thinking on the partial pressure. According Dalton's law, the total pressure of, for example, air is the sum of individual pressures. So if we have on the sea level, the regular pressure of air is 1 atm. There is 20% or 21% of the air is oxygen. And that's why the partial pressure is 0.21 atm. It's very simple. And the good point is that, okay, you don't even have to remember that how many moles of oxygen you have in the air, because everything that you need is the volume fraction. So if you know that, okay, there's 20% of the gas is because now we think that all these are working as ideal gases. Okay, in that case, it makes sense that, okay, now we can calculate that what is the partial pressure of oxygen in the air around us. And then we can calculate that how much oxygen there, what is the partial pressure of solution that is touching or is in equilibrium with the air around us. So when we have, for example, a water glass, it goes in the equilibrium with the air. So there are oxygen molecules that are dissolved in this aquatic solution, and it will remain the partial pressure. So in the equilibrium, in the water glass, you have the same partial pressure of oxygen as you have in the air. And this is a very good thing. That, okay, if you have shallow water, like some pond, there's as much oxygen in the solution, in the aquatic environment, as in the surrounding. They have the same partial pressure. But the problem is that actually this is a little bit it's more complex, because if you are calculating how many moles you have, it might be a little bit different. The problem exists that the oxygen or several other gases, they are not ideal gases. So in the low concentrations, this vapor pressure is a little bit higher. So we have Henry's law, again, very simple. Having the mole fraction, how many moles there exist versus the total moles of the solution, and then we have Emperor's constant to say that, okay, what is the pressure? And this Henry's law can be used to estimate, for example, how much oxygen you can have in the solution. So there are some limitations. Okay, we can estimate what is the molar solubility of oxygen at 25 degrees Celsius when the partial pressure around the water is 160 torrs. And then, okay, means that, okay, it's in equilibrium. Because the solution is dilute, we don't have to worry so much that there are more moles of molecules in the solution when we have oxygen there. because there's plenty more water molecules. And this makes just the calculation a little bit easier. And then we can just multiply the partial pressure of oxygen with the amount of water molecules and then divide it with this Henry's constant. And calculate that, okay, actually you can have only 0.3 millimole per liter of oxygen diluted in the solution. Okay, or we can use the same calculation or the equation for carbon dioxide. Now we can see that the Henry's constant is a little bit different. And this affects that now you can have 7 millimole of carbon dioxide in liter of the water or the solution. So which means then you can have not more than 8 milligrams of oxygen in the solution in these conditions, but you can have at the same time 300 milligrams of carbon dioxide. And this is important that now it can be understood that these solutions are very good to carry carbon dioxide, but quite poor on carrying oxygen. And that's why we have these red blood cells, we have these hemoglobins, etc. Okay, it's quite understandable. And okay, we can even then calculate that, okay, how much we have the same partial pressure in the solution as well as in the environment, and then we can calculate that, okay, how much oxygen there can be dissolved in the aquatic solution. But the problem is that the Henry's constant is different for different gases. Okay, that could be easily take in the account that, okay, you are using just a different value. But the problem is that actually this constant is not a constant. So it's a little bit oversimplification. It's a little bit bad science, but it's a so simple way to calculate it. So that's why we are using it. And one exploration was made by Van Hoff using the same Henry's law, and to understand that, okay, the temperature is affecting on the solubility. So over here you can see from the 0 to 40 degrees Celsius, there's less oxygen that can be dissolved in the fresh water. So it's temperature sensitive, this constant. And then we have a Russian scientist, Shehonov, that was describing that actually it affects on the salinity. So how much ions you have there. So in the seawater, you can have less water dissolved in the water than in the fresh water. So that means then that, okay, then you can, it's a little bit more complex, but anyway, it's then understandable that how much water, or you can measure or calculate how much water you can have, how much oxygen you can have in the water in any conditions. Okay, what about then in the daily practice? Can we understand this phase difference from the gas to dissolved and backward, etc.? Yes, we can make a very simple experiment. If you have a soda pop and open it and heat it up, there are more bubbles coming because in the warmer temperatures as much gas cannot be dissolved in the solution as in the cold. And if you are opening the hot or quite warm soda, there are a lot of bubbles coming quite fast. Or then another experiment you can make. If you have some carbonated solution, add some grains of salt. You are increasing the salinity and decreasing the amount of gas that can be dissolved there. And then you can have more bubbles coming. Quite simple. Thank you.